In this video, we are going to look at the inclined plane. Hi, this is Sean Huang from the Physics Department. If you have not watched the videos titled Vectors and Vector Addition and Examples of Newton's Laws, you can find the links down below in the description. This is a side view of an inclined plane, which makes an angle of theta with the horizontal. If the surface is frictionless, the object M will slide down the plane due to gravity. The question is, what will be the acceleration as the object moves down the plane? There are two special cases. In case 1, if theta is 0, then the plane is not inclined and the object will not move at all. In case 2, if theta is 90 degrees, then we have a vertical plane. There's nothing to support the object, and the object will be in a state of free fall with an acceleration of 9.8. So, the answer to our question would be an intermediate value between 0 and 9.8. This problem is easy if you can adapt to the geometry of the problem, which is uniquely determined by the angle theta. To see this, there are two auxiliary lines that we have to draw. The first makes a right angle with the inclined plane, shown here in red. The second makes a right angle with the horizontal, shown here in green. Once this is done, you can see that the two angles theta and phi will add up to 90 degrees, and that the two angles phi and theta prime will add up to 90 degrees as well. Line up the two equations and subtract one from the other, and we can see that theta is equal to theta prime. In other words, the angle between the two auxiliary lines, the red and the green, is the same as the angle of the inclined plane. Since they are equal, we can drop the prime and call the angle between the two auxiliary lines theta. This angle theta, however, is not taken advantage of by the usual x and y coordinate system. In physics and in chemistry, the solution to a problem can be simplified if we can choose a coordinate system that adapts to the geometry of the problem. Here, we will adopt a coordinate system that is tilted or rotated by an angle theta, so that the x-axis points along the inclined plane and the y-axis points perpendicular to the inclined plane. We then can see that in this new coordinate system, the object M moves in the negative x direction with an acceleration a. In other words, the motion, which was two-dimensional in the original coordinate system, has become one-dimensional in the new coordinate system. There are two forces acting on the object, the gravitational force and the normal force. Each will have to be written in its component form. For the gravitational force, we will draw an auxiliary line so that you can see a right triangle where we have shown that this angle is theta. And right away you can see that the x component is negative mg sine theta and the y component is negative mg cosine theta. The normal force is more straightforward. By definition, the direction of the normal force is perpendicular to the plane which the object is in contact with. Therefore, in the new coordinate system, the normal force has only the y component. We are now ready to apply Newton's laws. According to Newton's second law, the product of mass and acceleration must be matched by a net force, which in this case is the vector sum of the gravitational force and the normal force. So, equating the net force with the product m times a, we will obtain a set of equations from which we can conclude that the acceleration a is equal to g times sine theta, and the normal force n is equal to mg cosine theta. In summary, whenever we see an object on an inclined plane, assuming that there is no friction, then the object will move towards the bottom of the plane with an acceleration of g sine theta, and the normal force will be mg cosine theta. In the special case where theta is equal to 0, since sine of 0 is 0 and cosine of 0 is 1, we have a case of a still object. In the special case where theta is equal to 90 degrees, since sine of 90 is equal to 1 and cosine of 90 is equal to 0, we have a case of free fall. And that completes our treatment of the inclined plane.